Welcome to Lecture 25, General Relativity. In the last lecture, we spent a good amount of time talking about Einstein's theory of special relativity, which described how space and time are in fact combined into a four-dimensional space-time that's necessary to describe objects, in particular how they behave and how nature behaves when things are moving near the speed of light at relativistic speeds. But as I mentioned at the very end of that lecture, it turns out that that's not the end of the story, because special relativity is restricted to describing objects and frames of references that are moving with respect to one another at constant velocity. But as we know, that's not how nature works. Nature does not restrict itself to constant velocities. And in particular, given that this is an astronomy class, we're interested in how things move in gravitational fields. So we know when forces are exerted, accelerations result. And so we would really like to be able to describe things and how nature behaves and how objects behave when they are accelerating. And so Albert Einstein published his theory of special relativity in 1905. And essentially immediately afterwards, he set about to answering exactly this question, to generalize his theory of relativity into one capable of describing objects that are accelerating. And it took him a solid 10 years to do it. But in 1915, he published what is known as his general theory of relativity. So again, not very creative. He started off with a special theory and then spent 10 years generalizing it. And when he accomplished it, he said, okay, this is the general theory of relativity. And it turns out that that is his stood the test of time now for over 100 years. I told you that special relativity has been tested over and over again and has always stood up to the test. General relativity, same thing. We'll talk about some of those tests today. But it is and has been since then the theory of gravity. And so we're going to go ahead and dive in. So as I just told you, it took him 10 years to generalize special relativity into general relativity. And that is, for now over 100 years, the modern explanation of how gravity works. And general relativity, with one minor exception that I'll say something about. General relativity explains gravity in all situations. Newton's laws can be looked as a limiting, I say a subset here of general relativity. Probably would be better to say a limiting case of general relativity. So Newton's laws still provide very, very good approximations to the exact behavior of nature. And under a lot of our everyday circumstances, those are more than adequate for our purposes. But general relativity takes it further, is much more accurate, and that additional accuracy sometimes is important and sometimes isn't. Obviously, or if it's not obvious, I'll tell you, we're going to be interested today and really in the remaining lectures of this series in those cases, those exotic cases, those extremely large gravitational fields, for example, in which the differences between Newtonian gravity and general relativity are significant, and we like to see those play out. I will say the one caveat here with regard to this statement that general relativity explains gravity in all situations is that one of the biggest outstanding problems in modern theoretical physics is a unification of quantum mechanics with gravity, and that has not been accomplished, or more generally, quantum field theory has not been unified with general relativity. That's a problem. It's a problem that a lot of people are interested in, that a lot of people have spent a lot of time and energy on, without any observable success to date. So general relativity to date has been borne out and has stood every test that it has been given. But we know that when we get down to scales, to length scales on the quantum mechanical level, very, very small, right? We know that it will break down. For most applications, we don't care, right? Because when we're talking about gravity, we're usually not talking about gravity, the gravitational forces between electrons, for example. They're pretty small and swamped by electrostatic effects, among others. So for any practical purpose for you and probably for me too, frankly, and for almost anybody, this is not much of a limitation. But from a purely theoretical physics perspective, there is some ongoing work. General relativity does break down at the quantum mechanical level, but as long as we stay away from that level, which we do in this course, it is perfectly accurate and has proven correct in every test to date. So one of the most sort of the bedrock principles of general relativity is something known as the equivalence principle. And so I want to start by reminding you that special relativity told us that there's no way to distinguish between a stationary reference frame and a reference frame moving at constant velocity. Okay, we didn't state it exactly that way. What we said is the speed of light is the same in every frame of reference. But the result is that, well, if that's true, then there's really no way to tell whether you are actually at rest or if you're actually moving with constant velocity. Another way of saying it is that velocities are all relative. Okay, so when we say, oh, I was driving down the road at 30 miles an hour, what I mean is my speed was 30 miles an hour relative to the road, right? We often dispense with that relative to the road. We don't say that. We just say I was driving at 30 miles an hour because we all just understand that we're talking about the road's frame of reference. But in principle, it's an important distinction. And one of the results of special relativity is that, well, the result of nature, that's the way that nature was made again, as described by special relativity, is that there really is no way, even in principle, there's no experiment that you could perform that would allow you to determine whether you are actually stationary or moving at a constant velocity. Okay. General relativity takes it a step farther and says that a reference frame in a gravitational field or in a gravitational free fall is indistinguishable from those same reference frames. So in other words, there's no test that you could perform if you're in free fall to determine whether you are actually in free fall or if you're in a gravity-free environment. Okay. And in fact, that's why people will refer to being in orbit as being in 0G, right? You're certainly not in 0G, right? If you're orbiting in a spaceship, there's definitely gravity there, right? Because if there weren't, you wouldn't be orbiting, right? The only reason that you're orbiting the Earth in this space shuttle is the Earth's gravitational field. Okay, so definitely not 0G. So why do we call it that? Why does it feel like 0G when you're floating? Because you're in free fall. And the equivalence principle is Einstein's statement that there is no way, even in principle, there's no experiment that you could perform that would allow you to differentiate between gravitational free fall and a frame in which you had no gravitational field at all. So this is the equivalence principle, and it's one of the bedrock principles of general relativity. So now let's say something about space-time, because space-time is a concept that we introduced in the last lecture discussing special relativity, but it's of fundamental importance to understanding general relativity and understanding how gravity is generated, why gravity exists. So Einstein fundamentally recast the notion of gravity. So for Newton developed his theory of gravity based upon Kepler's laws, right? So Kepler looked at a whole lot of data taken by Tycho Brahe and poured through these, the data over decades, and eventually came up with his 3 laws of planetary motion. These were empirical laws. He had no explanation for why they were true. He just said, I look at all the data, and these 3 things are true. Newton then took those laws and said, well, let's assume there's some gravitational force, some attractive force between the sun and the planets that is causing them to orbit. What would that law have to look like mathematically? What properties would it have to have in order to give rise to Kepler's 3 laws? And by doing that analysis, he came up with his famous inverse square law of gravitation. But that's as far as he went. There was no description of, well, how does the Earth know that the sun is there and that it should be orbiting, right? it was what you might call action at a distance. It was a long distance force. So not a contact force, right? We kind of understand, or we think we understand. That's something worth pondering. We kind of feel like we understand when I push or I pull on something, how that force is transmitted. But it's much less clear for this long distance force between the sun and the earth, for example. And Newton didn't answer that. For Einstein, though, he completely reimagined this and says, no, you don't need some magical sort of means of communication between these two objects. Instead, gravity is going to be a natural result of a distortion or a curvature of space-time itself. Okay, so I'll say that again, and you can rewind it and listen to it as many times as you think is helpful, because it's absolutely central to general relativity, and it's central to what we're going to be talking about for the next little while. So gravity now is a result of curved space-time. And I'll say it, in another way, which is that mass makes space-time curve, and then the space-time tells the mass how to move. And we'll come back, I'll say that again here in a little bit. So let's begin by saying that far away from any source of mass, so any mass, as long as you imagine there's no mass in space or in space-time, then space-time can be viewed as a flat grid, and I've kind of shown you that here. Now, do keep in mind, we live in a four-dimensional space-time. This diagram is two-dimensional. It turns out it's really hard to draw four dimensions. Like, we can't. And so there are certain limitations there, but we really get I think we get a good picture just by viewing this reduced dimensional space. So this is a two-dimensional view here, and where there's no mass. Okay, so space-time is flat, and that is what it is. This line that I've drawn here represents something that's known as a geodesic, which is just a fancy mathematical term that means the shortest distance between 2 points. So you've probably heard the shortest distance between 2 points is a straight line. And when space-time is flat, geodesics are straight lines. So what you've always heard, that the shortest distance between 2 points is a straight line, is true in flat space, also known as Euclidean space. So when you took high school geometry, it was Euclidean geometry. And so everything you know from there is immediately portable over here to flat space-time. And all moving objects, including light, will travel along geodesics if there's no external force that accelerates them. And this is just a reformulation of Newton's first law. An object in motion stays in motion with constant velocity unless acted upon by a net external force. So this is just kind of, we're not saying, haven't said anything new yet. We've just sort of reformulated and restated some things that we already knew in terms of the language that Einstein has used in general relativity. But what happens when we add mass? So it turns out that mass warps space-time. It curves the space-time. And it does so in a way that that's visualized here in the bottom figure, but that you can think about as if you took a bowling ball and put it on a mattress or on a rubber sheet. And I encourage you to Google and find some internet sources. YouTube has a number of great demonstrations where they actually have rubber sheets or things where they put different masses on, and you can actually see this in real time, worked out. And I think that's helpful. But what you start off with is a flat space-time, and then as you add mass, that mass warps the space-time. So again, mass is telling space-time how to curve. And the more mass you have, the more curvature you will have. The result of this curvature is the geodesic that passes through that warped space-time is now a curved path and no longer a straight line. This shouldn't bother you too much, because if you've ever looked at a flight path of any significant distance, when you travel, if you fly to Europe, for example, you definitely don't take a straight line path, right? And the reason is that the Earth is curved. Okay, so a straight line in curved space is not the shortest distance between 2 points. And so in this case, once you add mass to the space-time, you curve that space-time, and now the shortest distance between 2 points is no longer a straight line. And so whereas in Newtonian mechanics, the first law stated that in the absence of an external force, objects move along with constant velocity, which in space-time means a straight line. Now, we've just changed that slightly. We've said, no, they don't travel in straight lines, they travel along geodesics. In flat space-time, a geodesic is a straight line. But in the presence of mass, when space-time is curved, those geodesics are no longer straight lines. But for Einstein, it's still true and remains true that objects travel along geodesics in space-time. And as I told you, this is not, it's a fundamental reformulation of gravity, to be sure. But the concept of non-flat or of curved space-times, curved space, is not a new thing. We live on a curved, on a globe, right? And so despite the fact that when you take geometry in high school, almost everyone learns only Euclidean geometry. There's enough there to take up, a year. There are a lot of other types of geometry that involve curved spaces, and that's, as I said, that's useful for planning flight paths, and it is certainly useful for understanding gravity. So as I mentioned a couple of slides ago, the more massive an object is, the more it distorts or curves space-time. And so if we look at the effect of, say, a low-mass star, it's going to introduce some curvature to that space-time. And so for a planet that is within the gravitational sphere of influence, if you will, of that star, if it's in the curved region, then it will orbit that star because it's on that curve, and the geodesic that it's in is a closed loop around that mass. On the other hand, if a planet is, or a planet or a comet or an asteroid or something is far enough away, then it may be slightly bent as it moves through space-time, but it will not be bound in a closed orbit. On the other hand, a high-mass neutron star in this case, is a much denser object, right? I mean, if you recall, the radii of neutron stars are on the order of 10 kilometers or something like that. So you've got, which means a diameter of maybe around 10 miles. So a really, small thing with masses up to, say, 2 solar masses, or something like that. So it's, a very compact object, huge density, really curves space-time a lot. And so this, again, gravity is completely, it's generated naturally by the curvature of space-time. And so all that mass does is it curves the space-time. So when the sun curves space-time, Earth doesn't know anything about the sun being there per se. It doesn't look out and say, aha, I see the sun, there it is, and so I'm going to feel a gravitational force. All physics is local here, which just means that Earth only responds to its immediate local environment. But that local environment means the local space-time. And so because the sun over there has curved space-time where the Earth is, the Earth moves on a geodesic in that curved space-time. And the upshot is it ends up orbiting the sun. And here's just another picture. This, again, there's a YouTube link here that I invite you to go to, and there are, like I said, there are lots of videos out there that may be helpful. Orbits are really circular or more generally elliptical geodesics, and there's no magic here. They just are the natural path that an object follows in the curved space-time. So it really is, it's a complete reimagining of gravity. Newton, again, didn't have an answer to the why of gravity. He had a great law, he had a great mathematical expression that was very, very accurate for a very large number of applications, but he didn't have a why. Einstein now reimagines this and provides a why. He says, objects, it's not this magical action at a distance, this long distance gravitational force. What we perceive as gravitation is just the natural response to being in a curved space-time. And so here's another sort of example here. If you look at a mass warping space-time here, and you imagine rolling marbles by this, the path that the marble will travel on depends upon how fast you shoot it and how close it goes to the mass. And so some of them may be caught in closed orbits and be stable, like the planets are around the sun. Others may be moving fast enough that they get curved, they get whipped around, but they don't get captured. And so that's something like, we have objects, all the time that will come by the solar system that won't get captured, but will get redirected as they move along the geodesics. And, I kind of alluded to this, but it's worth saying explicitly. The rules of geometry change when space-time is not flat. So I don't know how much you loved or hated geometry when you took it, but chances are, unless you've gone out of your way to study non-Euclidean geometry, everything that you know about geometry is Euclidean geometry. It turns out that that is the most useful for everyday applications for the vast majority of us. And so if you're going to restrict yourself to teaching, one type of geometry in schools, then it makes sense for it to be Euclidean. I do think it would be valuable to at least tell people that there are other types of geometry that are quite relevant. But when you move to these other types of geometries, everything that you thought you knew changes. And so, for example, on a warped sheet here, that would arise by virtue of a mass being present in space-time, the circumference of the circle will be less than 2 pi r. So you learned way back when the circumference of a circle is 2 pi times the radius of that circle. Well, that's only true in a flat space-time. In a curved space-time, such as is shown here, the circumference will actually be less than 2 pi r. And how much less it is, it turns out, is related to how much curvature that space-time has. So that's actually a kind of a cool property of this, and we're not going to go into much more detail than this. But it turns out that in a curved space-time, you can, by measuring, say, the radius and the circumference of a circle, you can infer how curved the space-time is. Whereas in a flat space-time, because the circumference is just 2 pi r, you can't get that kind of information. Similarly, triangles have more than 180 degrees. So you may recall, all triangles, the sum of the interior angles of a triangle in Euclidean geometry is always 180 degrees. Not true in curved space-time. In curved space-time, such as shown here, triangles will have sums of internal angles who are greater than 180 degrees. And in fact, how much greater than 180 degrees, again, is related to how curved that geometry is. So in fact, one way to determine, am I in a curved geometry, or am I in curved space-time or flat space-time, is to make a triangle and then go measure the internal angles and add them up. There's a great, I don't think that we're going to do that today, but you can certainly imagine doing this on the Earth, just by taking a walk and measuring out a triangle, walking along the paths of a triangle, and then measuring the internal angles and adding them up. It turns out you have to take a long walk before you start to be able to tell that the Earth is curved, but it certainly can be done in principle. Okay, so I've told you the basics of general relativity now, but I haven't yet told you why. Okay, so in general, in physics, new theories develop not for no reason, not just because people like thinking, though there is increasingly too much of that. That's not a good theory. The only reason to develop a new theory of physics really is that you have experimental data that doesn't match your current theory, right? If you remember back to the very beginning, very first lecture of this series, when we talked about the scientific method, it starts off by making an observation and then developing a hypothesis or a theory to try to describe that data. And then continuing to refine and test and refine and improve your theory. So what is it? Why did Einstein start reimagining gravity? And it wasn't just because he had an ego problem, didn't like Newton. Okay, there was data that was pushing him in that direction, and one of the most important aspect or pieces of that data is something known as the precession of Mercury's orbit. So, according to Newtonian gravity, if you have a planet, Mercury, and we'll focus on Mercury for a reason that I'll mention in a second. But if you have Mercury orbiting the sun, it will do so in an elliptical orbit, and it will be perfectly content to do that until kingdom come. Okay, it will just happily trace out that ellipse forever. According to general relativity, though, it'll actually do something a little bit different, and its orbit will undergo a process known as precession. And that's depicted here in the right. And that process is what it looks like. The elliptical orbit itself, while Mercury does continue to go in elliptical orbit, that elliptical orbit actually shifts over time by a predictable amount, a calculable amount. And so this is an important difference in the predictions between Newton's law and general relativity. And this is what we're looking for, right? Because, you know, it's no good if you have a theory that's perfectly good that explains all the data. There's no reason to develop a new theory, right? Some people will try to do that to get famous for, you know, but it's irritating because, you know, there are enough unknown things that we need to work on. We don't need to work on the known things or the theories that work. But at the time of the late 19th century, early 20th century, it was known, our instruments were finally good enough that we were able to measure the precession of Mercury's orbit, and we were able to get a good number for it. We were able to see that, yes, Mercury's orbit actually is precessing, and we were able to measure how much precession that was occurring. And so this was a very hard piece of data that was not explained by Newton's law of gravity, and so there was a good reason for Einstein to go forth and calculate. And as you might imagine, since we're having this conversation, when he did calculate, he got exactly the number that was observed. And so this was a very early and very phenomenal success of Einstein's theory of general relativity. But it's not the only piece of information. So another very powerful piece of data in support of general relativity is a phenomenon known as gravitational lensing. And again, continuing our theme of not being creative in our naming schemes, it is what it sounds like. Gravity actually acts as a lens for light. Now, it takes a lot, it either takes a lot of mass to do it or a really precise instrument. But one way in which this happens, for example, is if we look at two different stars out some, who knows how many light years away from Earth, they emit light in all directions, right? And some of that light comes towards Earth. Well, the light travels along geodesics, right? And far away from any mass, space-time is essentially flat, and those geodesics are essentially straight lines. But as those geodesics approach the sun, for example, on their way past the sun to the Earth, those geodesics get bent a little bit due to the mass of the sun, which warps its local space-time. And the result then is that the geodesic is bent, and the light ends up traveling in and striking the Earth, and so we can observe it. So when we go out at night and we look up at the stars, we see a star and say, aha, I see where that star is in space. But what you don't know is that, or what your eyes certainly don't know, is that sunlight, that light has not just come in a straight line towards you. It's traveled along a geodesic, and that geodesic happened to be warped in between the star and you. The result is that your eye, when your eye looks at something, it just your mind follows the light back from the direction that it came, and it sees star 1 in this apparent position, which is different than its actual position, right? And similarly, star 2 is apparently at this point in the sky, whereas its true location in space is quite different. Okay, so mass, you know, so far we've talked about the orbits of massive objects around stars, right? And we never said anything about light being bent by mass, but it turns out that gravity acts on light as well, through the exact same mechanism it acts on masses by curving the space-time. The reason that we don't observe gravitational lensing, or we didn't recognize gravitational lensing for so long, is, well, for one, it's actually really hard to figure out exactly where a star actually is, since you can't go out and visit it and say, hey, that wasn't where it looked like it was, what happened? We're stuck here on Earth, and so, if the stars are actually somewhere different than where we think they are, we usually don't know. But the other aspect of it is that light moves so quickly that that you only observe gravitational lensing if it passes through a very strong gravitational field where there's a lot of curvature of spacetime, or if you can you have the equipment set up to make very precise measurements. And in this case, we have observed gravitational lensing. Yeah, okay, so I already said that. We have observed gravitational lensing in a few different ways, but one of the most phenomenal tests of it happened very early, 1919. So only 4 years after Einstein published his theory of general relativity, there was a solar eclipse. And the reason a solar eclipse is really useful for making this type of measurement is that usually we can't observe stars that are near the sun, right? Because the sun is a whole heck of a lot brighter than any other stars. And so during the daytime, we don't see the stars, right? But the only time that the sun could even conceivably lens light coming to us from other stars is when that light is passing by the sun, right? At night, when we're facing away from the sun, the light from the stars is coming straight at us. It doesn't pass the sun. And so no lensing will occur. If we want the sun to gravitationally lens distant starlight, we need that light to be passing by the sun, which means we need to be making the observation during the day. So the question then is, well, how on Earth can we manage to make observations of distant stars during the daytime? It turns out the answer is during a total eclipse. So during a total eclipse, enough of the sun, the sun is blocked out, and it gets dark enough that we actually can observe the positions of distant stars. And when you do that, you can see in this particular picture, which is it's a phenomenal picture once you know what it's showing you. It's a superposition of two images of the sky, one before the eclipse and one after the eclipse, or during the eclipse. Presumably taken different days, so it's taken at exactly the same time during the day. So the stars, the stars are in the same location relative to the Earth, and then you see a very clear shift in the position of these stars. And so you say during the true position of the star is here, for example, but during the eclipse it showed up here because it was that light was gravitationally lensed by the presence of the sun. And this is, these are very rare instances in science where you have a revolutionary new theory completely, reimagining something with a very clear prediction, where everybody kind of comes together and they know, okay, this is when the test is going to happen. In fact, there was an earlier test prior to 1919. I don't remember if it was 1918 or 17 when they had planned to make this observation, but it turns out that on the day of the eclipse, it was cloudy, and there were no good. Nowhere in the world was able to get where the total eclipse was occurring was able to get good enough data to actually do the test. So the real test was delayed until 1919, but then overnight Einstein becomes a celebrity because again he's completely reimagined all of mechanics. So he's already done special relativity. So within the scientific community he's certainly known, but it was really his success of general relativity and that catapulted him to becoming the first international scientific celebrity, I think, that had ever existed. And so here's another schematic that kind of shows the same process. So here the Earth is in the lower right hand corner, and you can imagine having a galaxy very far away, and then in between the Earth and this far away galaxy is some large mass. What that large mass could be a cluster of galaxies, as it's indicated here. And what will happen is that the light from that distant galaxy gets sent out in all directions. But the part of that light that happens to travel closely or within the geographical region of influence of this galaxy cluster will be lensed, right? And so you'll end up with light from the same galaxy bent in different directions around this galaxy cluster and ending up at Earth. And so this is a really cool effect then, because the result is that when we look up in the sky, we're going to see light coming from two different directions. These two orange rays are representative, that actually comes from the same galaxy. So we're going to see the same galaxy in two different parts of the sky because it's been lensed from different directions. And in this schematic, only two distorted light rays are shown, but you can imagine there actually are lots of other ones too that go above and below and at all angles around this galaxy cluster. And the result is what's known, appropriately enough, as an Einstein ring. And so I can't imagine what it would have been like to make this observation. I don't know for sure. I assume that this is taken by the Hubble Space Telescope. But what you see here is you see this ring. Well, this ring is just lots of smeared out copies of the same galaxy. So you've got some central mass, this is all very far away. But you've got a whole bunch of mass here, and then you've got a galaxy way beyond that on the other side of that central mass from us. And so, this is probably a galaxy cluster, a very massive galaxy cluster. And so all of that light from that distant galaxy is being bent around and then brought back together to Earth, traveling along geodesics. And so you get this ring in the sky that really is just a single galaxy, say, or maybe a galaxy cluster itself. But it's essentially a single entity very far away that, strictly due to the gravitational lensing thanks to the warped space-time, we see this ring. And so this is an extremely famous picture, and there are others like it. Every once in a while, you'll see things like this show up in the just in pop news as well, because astronomy gives great pictures, and this is certainly one of them. So yet another piece of evidence in support of general relativity. Okay, so let's continue with more. If I haven't convinced you yet that general relativity is true, let's continue on. So another piece of data that we have collected and that continues to support general relativity is a phenomenon known as gravitational redshift. So we've talked about redshift in the context of the Doppler effect, where the wavelength or frequency of a light source, or any other wave source for that matter, depends upon the relative motion of the emitter and the observer. So if an object is moving away from you, the light it emits will be redshifted as you receive it. But it turns out there's another kind of redshift, which is known as gravitational redshift, which essentially comes down to the fact that it takes energy for light to climb out of the well, which is generated by masses in the warped spacetime. And so if you've got some central mass here, and think of it as a neutron star, for example, or to a lesser extent a white dwarf, something that's very dense, so you'll have a lot of curvature, so that you'll notice the effect. Light, as it climbs out of that well, it takes energy to do that. And so if you started off as a blue photon, say a high energy photon, you have to give up some of that energy in order to escape the gravitational well. And when you do that, you get redshifted down to, say, maybe a yellow photon or a green photon or something like that. And that's just because you can't, if you think about a massive object, you say, well, I understand that, if I throw an object up in the air, as soon as it leaves my hand, it starts slowing down, right? It loses energy as it climbs up the gravitational potential well. You may not think of it, but you're losing kinetic energy as you climb up. If I throw that ball fast enough, greater than the escape velocity of the Earth, then it will escape. But once it escapes the Earth's gravitational field, it will be moving more slowly than when it started. But light can't do that, right? Light can't slow down because special relativity says, and it's still true in general relativity, light travels at the speed of light. And so if it can't slow down, how does it lose energy? It lengthens its wavelength. And so light that is escaping from very massive objects will get redshifted because of that loss of energy. Guess what? We make the observations, and indeed, that's what happens. If we take a normal star, and this is, I don't know if you'd call this a normal star actually, it's a normal high mass star apparently since it's blue. So you take a normal blue star and it sends out its light, and we see blue light. Okay, that's not a huge surprise. We spent quite a lot of time earlier in this series of lectures talking about all of the information that we can gain about a star, its temperature, the pressures, the composition, and so on, by looking at the spectra that it emits. Okay, so blue star emits blue light. If we take a white dwarf, though, imagine a white dwarf whose surface temperature is such that it's emitting blue light. That light's emitted, but the object is so dense that the curvature of space-time is so large that a non-trivial amount of that energy of the emitted light is taken away just by climbing out of the gravitational well. And so what started off as blue light may get shifted down to green light by the time that it actually escapes the gravitational influence of the white dwarf and continues on its merry way through space to Earth. So this is another layer of confusion that can be added in to all of the spectral analysis that we already talked about some time back. Because we observe this, we say, there's a green star. What on earth is that? Well, it turns out that light wasn't green when it was emitted, but it was redshifted by virtue of having to climb out of that gravitational well. And it can get even more extreme if you look at something like a neutron star, which is yet more massive and smaller, and so the curvature of space-time is even larger. It may, if there were blue light emitted from the surface or nearby a neutron star, it could be shifted all the way down to the red end of the visible spectrum. And so this is, gravitational redshift, as with most aspects of general relativity, is only observable when you have very strong gravitational fields. But fortunately, we've got the instruments to make those observations now. And as I've said over and over again, Einstein was right. And we're not done, because it turns out that there's also a case of time dilation in general relativity. So in our last lecture, we talked about time dilation in the context of special relativity, namely that the faster you are moving, the slower your clock runs. Well, it turns out that the gravitational field also influences the rate at which time passes. And time runs more slowly, deeper, or in a gravitational field, or in a stronger gravitational field. And this is actually, as long as you've got a couple of atomic clocks, this is actually straightforward to measure and has been measured. So if you take an atomic clock and you put it up in the mountains in Boulder, Colorado, where the gravitational field is just a little bit weaker, because you're a little bit farther away from the Earth's center, than in Greenwich, England, for example. Then you make very precise measurements of the time, and you find that the atomic clock, atomic clocks do not agree. Time really does run more slowly when you're in a stronger gravitational field. So I guess that means if you want to stay young, go hang out near a neutron star. The only problem is that it's hard to get away from it once you get there. So weigh all the options. But this is not just purely hypothetical. So a lot of this has been hypothetical. To some of you, you may have seen completely hypothetical. I'm a theoretical physicist when I get the chance to be one. And so all of that is perfectly fine with me. But some people are more practically minded. This actually makes a big difference. And it makes a difference in GPS satellites, which you may not think about knowing or using, but you use all the time. Anybody walking around with a phone, you want to use Google Maps or any other map app, or any number of other apps on your phone that are constantly getting your location, whether you know it or not. All of these have to take this into account, the effect of the gravitational field, in order to stay correct. And so general relativity, we've just learned that time runs more slowly when you're in a stronger gravitational field. Special relativity tells us that time runs more slowly when an object is moving fast. Well, now we've really outdone ourselves because we put these GPS satellites up in orbit. They're orbiting quickly, so that means time is slowing down, but they're also in a weaker gravitational field than we are here on Earth, which means the time is running faster. So which wins, and by how much? And so fortunately, we understand the theories of special and general relativity now. We can do the calculations. And when we do the calculations, we find out that the effect of velocity is less than the effect of gravity. And so the total correction that you need to make is in the direction of gravity, as it were. Because the point is that we care about the clock on my phone staying correct, right? I don't care about, the clock on the the clock on the satellite needs to be right, but it needs to, fundamentally, I don't care about what the time is doing up in orbit. I care about what the time is doing here on Earth. And so we do the calculations, we make the corrections, and it's all built into the, to the networks and the software that finally give your phone the time. But I just tell you this to say that this is, most aspects of things like special and general relativity are irrelevant to modern technology, at least as they're usually instantiated. Not here for GPS satellites. If you didn't take this into, these effects into account, the time on your clock or on your phone would get more and more wrong as time went on. And in particular, just to give you some clear numbers, the effect is 38 microseconds per day, and so that adds up over time. And there is one more piece of evidence for general relativity that I'll mention that is actually in the news quite a bit now. You may or may not have run across it, but if you look for it, it's out there. And that's something known as gravitational waves. The theory of general relativity predicts that gravitational waves will exist, ripples in the fabric of space-time itself. Now, in order to be noticeable or measurable by any conceivable device, they would have to be generated by extremely strong gravitational sources. And in particular, that means things like black holes and neutron stars that are just extraordinarily dense and colliding. And so, 20 years ago, maybe now, there was a device known as LIGO, Laser Interferometer Gravitational Observatory, that was built. This is just extraordinary piece of modern technology. I say piece, I mean it's huge. So I encourage you, Google LIGO, LIGO, and read up on Wikipedia. But anyway, the upshot is that it was designed to make very precise measurements of ripples in space-time that would be generated by colliding black holes or colliding neutron stars or black hole colliding with a neutron star. And it turns out that it observed them. So this is yet another result that, it was predicted by general relativity. Nothing else, no one else had ever conceived of anything like this. For the longest, well, for 100 years, there was no chance at all to actually make the observation. So sometimes this will happen where a scientific theory will make a prediction that you just don't have the technology to check. And it took 100 years to get it. But when we got it, at the risk of sounding like a broken record, Einstein was right. And so it turns out that now we're making, I remember when the first observation of LIGO was made, it was really, truly remarkable. One of the fastest Nobel Prizes in physics that I have ever, that's happened in recent memory. And there's plenty I could go on and on about that. So I won't, but I encourage you, if you're at all interested, to go Google that up and see what you can learn. So I told you that LIGO was big, and here's a bird's eye view of it in Hanford, California. You can see that the end station is 4 kilometers away from the base station, and there's another arm here. And so interferometers, incidentally, they're worth studying on their own. They've been used in a lot of cool experiments historically. This is certainly the largest one that I'm familiar with, but there it is. And here, just I told you that the first observations were really phenomenal. Came in February of 2016. So if you feel like sometimes science is not progressing very quickly, this is a case where it pretty darn quick actually. So there's a link to a video as well that I hope is still up because it was a good source. And I won't go through all the details here, but basically this ringing, as it's called, represents the fact that space-time really was wiggling here on Earth at a level that you and I would never have observed, but with LIGO we can. So thanks for your attention. I know we had mind-bending stuff with special relativity. We now have more mind-bending stuff with general relativity, but we're finally to the stage where we can now start talking about cool things like black holes and neutron stars in more detail. So thanks again for your attention, and I look forward to seeing you back next time.